Okay. So, the last thing we have to do in 6.3 is introduce a new type of function. So I think that there's only a couple new functions we've added to our list. Most of the stuff is just stuff that you've seen since Algebra 2 and Pre-Calc. What were the other new functions that we added the other day, just to remember? We had sinh of x. What was sinh of x really? Because I'm sure you'll see it probably next year a bunch, if not this year.
E of x minus the negative, over 2.
And then cosh
was negative e to the x plus e to the negative x.
It's just an average, right? So those are those nice combinations of exponentials. And why are they called like sinh, cosh, and then you can combine them and create like tangent, tang, and so forth? Because they have the same pairing properties with derivatives, and they have the same kinds of identities as the trig functions. That's why they were given these names. I mean, there's more to it than that in terms of the h. What's the h stand for?
Hyperbolic.
Hyperbolic. Okay, so we're not going to get into that too much, but you can just treat them as combinations of exponentials. So here's another new function that I don't believe you have seen before. It's called the logistic function. So logistic functions are something you definitely could have done in pre-calc. It's just, there's only so much time. A logistic function has this kind of shape. It's a very common type of thing for certain types of applications like the one we're going to do. So those of you watching the video, make sure you're watching, you're looking at example 10 in the textbook on page, what was it? 428. Perhaps look at that a little bit before you watch this video. Pause it now. So what is L? For all logistic functions, you have this L, which is like an upper limit. So in example 10, what kind of thing are we talking about for an upper limit that might happen?
Maximum sustainable population.
Yeah, it's like the maximum population. Was it elk in that example?
Yeah.
So it's like, in biology, they use this word a lot. So this is a very common biological type of function. They use it all the time in biology. So it's called carrying capacity, yes. It's not just biological systems that involve logistic functions, but they're pretty common in biology. They're common in other places too, like traffic. I've worked with traffic differential equations, which had logistic properties in them as well. So definitely a class of function to know about. Can somebody flip through the book and tell me the general form of this function? What is the form of it? It's not like so unusual. You guys have seen stuff like this a bunch in Calc this year.
dy over dt.
Ah, that's the differential equation. I want just the function, like the solution to it. I'll tell you. It's the carrying capacity divided by 1 plus some other constant. And it's basically just some kind of like transformed exponential. You can kind of see that it's like exponential. What's the only difference between this curve and an exponential curve?
This one's got a top.
This one's got a top. It's kind of like a combination of two exponential curves. It like grows exponentially until it hits this guy. And then it like decays exponentially up to that top limit, the carrying capacity in biology. Okay? What is this guy called, calculus students?
Oh, I know. Deflection point.
Thank you, Chance. An inflection point. Where do we find inflection points usually? We set the second derivative equals a 0, right? So a little bit of good review there. So if we wanted to find that point, would our calculator be very good at finding this spot? It can do maxes and mins, right? Can it find those? Not unless we write a program for it maybe or something. It can't do it right now. So we'd have to take double derivatives and set it to 0, which we could certainly do. That'd be a nice exercise for another day to review, maybe Monday or something. Okay? But right now, I just want to finish example 10. So what do they ask us to do, part A?
Yeah, but I mean,
okay, so the model for the elk population is that the population, why am I writing a derivative here? Why is this a differential equation? Because the population's changing in time, right? It's changing in time. That means there's some rate of change, which means it's probably a differential equation. Anything that changes in time, unless it's really, really simple, is modeled by differential equations, okay? So then it's going to be dependent on the original population, some kind of constant there. And then did they just give you the rest, or I forget how they phrased it? They just give it to you?
They just gave it to us.
They kind of just gave it to you. So for some reason there's that term in there. Let's not get bogged down in that. We'll just say they gave it to us this time. Okay. 4,000?
Yeah.
Okay. So that's a differential equation. Looks like it should be separable, doesn't it? Can we separate it?
They also give
It's
you
already
parameters.
separated.
It's it. Not,
Oh, what?
There's no T at all.
how would we separate it
No,
and
we
solve
just
it? Let's
divide
solve
it.
it. So let's solve it. And they gave us. Did they give us some about some conditions that we
Yeah.
can do?
Just divide them all.
P has to be between 40 and 4,000.
I want some initial conditions though. Some things that we can use
0
later
and
on.
40?
Yeah.
So how should I write that? Good. P of 0. T of 0. What?
When P of
P is 0.
Okay, that's one initial condition. Do they have any other conditions that they gave us?
P of
After 5 years.
5.
It's 104.
After 5 years is 104. That would just be like measuring the population, right? So they'd have to get a couple measurements. Why do they need more than one initial condition on this problem? Why would we need that to come up with a solution to the differential equation?
Too many variables.
We've got too many
Constant.
constants, right?
Yeah.
So they measured and told us after 5 years there were 104 elk or whatever.
Too many.
This is like in Yellowstone or something, right? I don't remember. No? Okay.
A game refuge.
So let's show that the solution to this differential equation is this logistic function up here. That's our goal. Okay? So someone, I mean back in, who knows, maybe like the 20s or something, realized that this was the kind of variation that they were seeing in the elk population. They formed it into a differential equation and they solved it, and this is the solution that they came up with. So let's go through that same process that whoever did this, I don't know, in the 1920s or 1800s or whenever, that they did this for the first time. Okay? So hopefully we'll get that kind of a shape. So let's just go back to where we were in calculus. Solve this differential equation. Okay, so can you guys help me with that?
Divide all of that stuff.
So we're going to get 2p over all that stuff, right?
All of them, except for K.
Let's leave the k. We could put the k over there if we wanted to, but we certainly don't have
It'll
to.
probably make your life more difficult. So.
It probably would.
Leave it
So
over.
k dt, right? Alright, so now we should just integrate. So the right hand side is going to be easy. The left hand side is certainly another story.
Here.
So this is kt plus a temporary constant. Now the left hand side. Do you know an integral that will do that?
Isn't there like a sign or something?
If it were to be squared,
Yeah.
But it is.
Todd, can you help us out?
What?
well, you call
We
it
need
just
to know.
P squared,
1 minus P squared.
right? Because it's one of those inverse, like
Inverse hyperbolic.
Yeah, but you'd have like
cotangent.
p minus p squared, wouldn't you, if you distribute?
It's the inverse
Well,
hyperbolic
is there-
cotangent.
Oh, does a hyperbolic cotangent work for this? I don't
Yeah,
know.
it's
I think
exactly that.
Something does.
With 4,000 in there. And, well, no, never mind.
I'm not sure. I don't think
Not
so.
quite.
There might be another way to do it, though.
Close.
Todd, what do we do?
I don't think that's a standard integral.
Help us.
We need help, Todd.
U sub?
U sub won't work. There's no U that will do this.
Integrating by parts.
You could maybe go with the table. I bet this isn't in the table,
It would
though.
have to have a square root.
Yeah. So if you do the square root.
Look at the bottom.
Minus p squared. Wouldn't, could you do an arc secant?
No.
Good guesses, though. All good guesses.
If you try distributing with P.
Todd should know. Todd should know. Oh, no. Can we clean that up? Let's make this be a common denominator, and then Todd will probably be able to tell us. Let's clean that up inside, shall we? What's that going to be if we make a common denominator?
P minus P. Oh.
4,000 minus P.
Okay, so then we'd have like P times 4,000 minus P over 4,000. We have like 1 over that. What if that was just 1 over p times p, Todd? Or 1 over p times p plus 3? How do you do this?
I'm not in the integral mindset.
I know.
We need you, Todd.
You use that.
Do we remember doing things like this for this situation?
Yeah.
This is called
Fraction.
good, Paul.
Partial fractions.
Partial fractions. Good, good, good. I love partial fractions. They're so much fun. This is not a super easy partial fractions question either. The book just like says, oh, do it by partial fractions. It doesn't show it, but we need to do this. So let's do it. Okay, so how are we going to do this? We're going to go P, we've got 1 minus P over 4,000 equals A over P, right? Plus B, these are both linear terms, right? And how did we make that a common denominator a second ago? We said it was
4,000 minus p.
right? Ringing some bells?
A little bit into
That's been too long. Of course, we'll do this again next year
I was hoping it
when
would
we
work
really
back.
need it. Okay, so what do we do next on partial fractions? There's lots of different ways to do it, but I like to select convenient values. So first, let's just multiply through by the common denominator. It's just an equation, right? So multiply through by the common denominator, which is this, isn't it? So you get 1 equals what's going to be left here? A times
One
the
minus-
P over P cancels.
Or you can do the common denominator if you want.
I could do the common denominator expression, that's true. Let's just leave it like that, shall we? Plus B times, when we hit it with that denominator, what's going to be left? P. Yes? And then we select convenient values. So what will be some convenient values of P which would knock things out?
0.
0. So we say, okay, that would be 1 equals A, that part would go away, right? Times 1 minus, what's 0 over 4,000?
So
0. So what is the value of A? We're making progress. Okay, what's another convenient value? That was an easy one to choose.
4,000.
4,000. Why'd Brenna pick 4,000?
Because that
Make that fraction go away.
That'd be the 1, and then you've got 1 minus 1. Very smart. So we're going to say that's going to be 1 equals A times, that's going to be 0. This is going to be B times, what's P again? 4,000. So we're going to have 1 equals B times 4,000. So what's the value of B? 1 over 4,000, right? Write it like that. Okay. Why do we do this?
So that we can now integrate.
So that we can now integrate, right? Let's see if that's now an integral we can do. This is a Calc 2 technique, partial fractions, and this isn't like the easiest example I started with either, right? Would I do this with most classes? Probably not. I'm doing it with you guys. So, let's see. So we're going to go 1 over what? 1 over P. Paul called this, when he remembered the technique, he remembered that it was called fractional decomposition. Why did you learn that? You learned it for this purpose right now, because this integral is not something you could have done otherwise. You're decomposing that fraction into a simple thing. What's the integral of that part going to be? Natural log. You know that, right? And then this part, I think we'll also be able to do. It looks a little ugly, but we're going to have plus what?
1 over 4,000 minus p.
And then this part, when we did the common denominator, would be,
I think that reduces to 1 over.
it does, right? They're both divided. You could flip it or do it however, but they're both divided by that, so that cancels out. And this is going to be equal to the integral of 1 over p plus 1 over 4,000 minus p. Can't you do both those parts, guys? Yes, you can. So we're going to get natural log of p. What's this one going to be? minus, you hear Sam say the minus, very good. Natural log of,
4,000.
I keep losing space. I'm sorry.
Lost in translation.
And that's implicit, right? So how can we make it explicit? Can we? There's like 2 P's in 2 spots. How can we do that?
Properly we can divide.
Yes. Can use that logarithm property. So this becomes 2 logarithms become 1 logarithm with P divided by 4,000 minus P. Make sure I don't lose a 0 this time.
Now you can eat it.
Now I can eat it. Need more space.
The greatest turbo.
Bye, partial fractions. We'll see you again next year. Okay, so then we've got P over 4,000 minus P. What's that going to become? Yes, you guys are fast today. I like it. And we're still not explicit, are we?
There's a
So how can we make it explicit?
There's only for T or P.
We want to solve for P, right? To like get the population as a function of time. Well, we could use this right now. This would be usable. We can use it right now. Plug in our initial conditions. But we wanted to see this come out as a logistic. Does it look logistic yet? I don't think so. Let's see. What else did I do? Oh, I said solving for P produces. That's not very good. How can we solve for P on this one? Oh, just this guy over here.
Clever one.
Full thrown out tactics.
Solve complete square.
And then divide by that again.
Pull out a P.
Then you have the T.
Okay, it's okay, guys. You pull out a P and you divide. It's okay. It's all gonna be okay.
Oh my goodness.
Okay. I have any mistakes? Keep my work. Is that looking more logistic now?
Yeah.
I think it is. What's the carrying capacity we think for this particular problem of it with elk? 4,000. So I don't think it's quite logistic yet because we like have this guy in there. How do we get it to be logistic? And this is just something people have done over the years to kind of clean up the equation and make it a little easier to do stuff with. How do you get that to logistic?
Change the KT.
One more step. You can't just change something to negative, Paul.
Write it as negative and put it on the bottom of the fraction.
Ah, so how do I make that happen? I think. Can we multiply by clever 1?
Just change it to
Yes!
Yeah, cool.
We can multiply by clever 1, can't we? I think that'll produce the form that we saw a second ago that was like f of x equals L. There's our L. So now this is going to cancel. You're going to have 4,000 over, what's going to happen here? This part's going to be 1 over CE to the KT. There's your negative, Paul. And this part's going to be, and when we saw that before, didn't it look like backwards? It was like 1 plus CE to the negative K over T. Yes! The logistic equation in all of its magnificence.
This is why I don't like him.
What?
Just kidding, just kidding.
You said this is why I don't like you.
Calc.
Oh, elk.
I'm not sure if you said elk or elk.
I thought it said
You'll
Z
never
at first.
know.
I was like, ouch.
This is why I like calc.
Calc's exciting.
Okay, so we had some initial conditions. Let's actually find the particular curve to fit this group of elk. whether Paul likes them or not. Okay, so which one would be nice first? The 0 one, was it 040? E of 0 equals, is it 40? Okay, so we're going to get 40 equals 4,000, 1 plus c e to the 0, and that's going to go to 1. And I'm not going to show you all the algebra, I'm just going to say what c is, okay? So let's see. C is 99. So I solved that and got 99. And the next initial condition we had was 5 and 104. So we go 104 equals 4,000, the carrying capacity. So apparently the land can only sustain 4,000 elk at most, no matter the conditions here. 1 plus 99e negative k. How long was that? 5. And then we solve that for k. I'm not going to show you the algebra again. I got about 0.194. So now I can stick this in. And I have my specific function modeling these elk. That make sense?
Okay, so that,
What else did they ask us to do with it? Let's just look at what else they asked. Graph a slope field. Let's just leave that. I'm going to give you a program before you leave here for your calculator, so you can do slope fields with your calculator. Because this one, do you think you want to do a slope field by hand?
No.
Go back to the original equation. I think that would suck a lot. So let me give you a program for that. Okay. What else did they ask?
Estimate the population after 15 years.
Is that going to be hard? We have the function now. What are you going to do? Plug 15 in after you stick those constants in, right? That's easy. Part D.
Find the limit as the model as t approaches.
Find the limit of the model as t approaches infinity. We could do that with algebra, but what would be smarter?
Just look
Look at it. What's the limit going to be?
4,000.
4,000. With algebra, if we stuck in front of this guy the limit as t approaches infinity, a very good question. That's what the biologists might be interested in. How many elk can the land actually possibly carry? You guys see why it's a carrying capacity?
You're essentially going to be dividing by 1.
Yeah, this is going to be
0.
negative infinity. What's e to the negative infinity?
0.
That's like 1 over infinity, isn't it? So that's 0. So this part's 0. What's 4,000 over 1?
4,000.
4,000. Do we see that? Is that okay with all of us or not? Let's see. So you go e to the negative infinity. That's 1 over e to the infinity, which is 1 over infinity. Okay? All right.
Times c.
We're done. I had fun. I hope you did too.